Welcome back to PC1, and this is the GT50 test facility. Over the course of the last few months, our magnificent team have developed 438 high complexity, precision gas turbine prototype parts from raw materials and first principles. To do that, they've had to complete no fewer than 71,668 machining operations and production operations. Of that, they have completed 99.5% of those operations, and we have the last few finishing touches to do to the last 20 parts. That means that in about a week and a half's time, we'll be able to assemble the very first GT50 prototype, and once that's done, light the fires and start the testing. In the last AMA, we featured a lot about how we're balancing the gas generator rotor. So this thing spins at approximately 50,000 RPM and has to make sure that the mass of the whole rotating assembly is very precisely located on the axis of rotation. We got that set up really beautifully. It balanced nicely on the machine. The next step is to make sure that when we disassemble and reassemble the rotor, it maintains that high level of balance accuracy, so that when we build the engine, because we have to essentially encapsulate a lot of these rotor parts around the engine casing. So we have to disassemble the rotor and then build it back up in situ in between the casings when we build the engine. So we've been doing a bunch of work on that recently to make sure that process is robust, so we don't have any nasty rotor dynamic surprises when we run the first engine. So that's all worked really well. We've got the balance land validated, we've got the rotor balanced nicely. It reproduces the balance point robustly when we assemble and disassemble. So we're all really pleased with that. Let's go and have a quick look at how we've modified the turbine disc and the locking plates to make sure that the turbine rotor blades are located in the rotor disc axially really tightly. So as you'll recall, our turbine blades are secured into the turbine disc using a fir tree root. Now the fir tree handles all of the centrifugal load when the disc is spinning at approximately 50,000 RPM, but we have to secure the blades axially in these slots, and to do that we use these little peened pressed metal clips, and what we do is they slide in and then we bend both ends over to lock the blade into position on the disc. Now that's critical for the balance of the disc, so it's really important that they don't move. Now the original design of that clip was a simple rooftop shape like so, that just fits into the bottom of the blade like this, and then we bend the ends over. The problem with that is the little rooftop feature itself rolled one radius into another, and it wasn't easy to hold the tolerances on those to keep that snugly up against the sides of the cutout in the bottom of the blade. And what we found is when we assembled the whole rotor, there was a lot of variation blade to blade in how much freedom the blades had got axially. So in order to resolve that problem, we've updated the design of the blade clip and redesigned the bottom of the turbine blade, and that's actually been included in the test engine rotor. Let me show you. So we've actually replaced the blade clip with this new design blade clip that looks a bit more like a tuning fork. Okay, and the idea with this one is because we can essentially laser cut, stamp or wire erode that profile, we can get the flat ends of the tuning fork pieces to locate really accurately in the groove in the bottom of the blade. We can use a simple press tool that we've manufactured here to then stamp the curved profile into these things so it sits snugly under the blade. So that's the flat one, and then that there is the pressed one. So we press the rooftop into it so that these tangs are what locates on the side of the blade, and then we press one end in, and then we just bend manually the far end when it goes into the blade. And this has made a huge difference to how we can locate the blades within the disc. So this is the latest production disc. These are our latest turbine blades, and these have all got the new locking plate in, and they're now completely secure in the disc, and they're sitting there nice and snugly, ready for robust balancing. To give you an idea of the level of detail that we have to go into to make this engine work properly, if you consider that new spring clip that we've created, at the ends of the tuning fork features that locate in the groove, we can't actually have sharp corners there because it would scratch and damage the turbine disc and the root of the blade. So we've actually had to find a way to put the tiniest of fillet radiuses on there to take those sharp corners off. Now to do that, we use the rumbling machine over there, where we use abrasive media to just remove the sharp corners without changing the bulk physical geometry of the tool. And when you get this under a microscope, you can see that after that processing, we've eliminated all the sharp areas that would otherwise be hazardous to the integrity of the disc. One of the final tweaks we've made to one of the other rotor components is, do you remember a couple of weeks ago I told you that we'd swapped out some slotted holes for round holes to improve manufacturability? Well, we did that and that worked a treat, but what we found is, because that changed the order of some of the manufacturing operations, when we subsequently went back and measured the curvic couplings, the changes in manufacturing processing order had thrown the curvics out. So we've had to make a new one of these with an updated processing order to keep the front and back curvic geometry accurate to the extent that we need it. So what you can see here is they're just putting the finishing touches to the curvic on the front end prior to switching this round and doing the final curvics on the back. And that's the actual one that's going in the test engine. So a couple of other components that we've recently completed as well are the key elements of our high-speed gas generator bearings. So this is the outer race for the gas generator rear bearing. So this includes the spring bar. This is essentially the suspension system that attaches the bearing back to the structure of the engine and controls the stiffness to manage the rotor dynamics of the gas generator rotor. Now this component single-handedly manages a lot of the axial load in the engine. It's the inner race of one of the high-speed bearings, and this flat surface on the outside is also the surface that we seal against to create the squeeze film damper that provides the damping for the rotor dynamics in the engine. Now this component is a complex one to design, a really difficult one to manufacture, and the guys have hit all of the tolerances for this. So this outer raceway for the bearing is well below a micron in terms of its roundness and cylindricity. It's an incredible piece of engineering. That's 1,000th of a millimeter that we're holding the tolerances to on this. And then similarly, we've got the cages that hold the balls and the rollers within the bearings to make sure they stay exactly where we need them when they're spinning at close to 50,000 RPM. Of course, the other magic ingredient to our rolling element bearings is the rolling elements. So these are the very first rollers for the high-speed bearings, and these are the very first precision balls for the high-speed bearings. And all of these components have to be made out of a really specific steel so that they maintain their strength and their hardness during the searing temperatures and the high temperatures that you see at the core of the engine under various conditions. So really pleased to have these in. These are very, very difficult things to make well also. And then it gets really exciting because now we can start to show you some big bits of engine. So this is the front structure of the engine. This is the inlet casing. That's the back face of the accessory gearbox casing. So these bosses are where the gears and the bearings attach. And this center portion here is the bell mouth that draws the air in to the inducer of the impeller. And then the back here, this is where the inlet shroud attaches with the abradable. And so this arrived a couple of days ago, and we're just about to get this on the 5-axis to dress all of the mating flanges so that this will connect neatly to all of its sister components. The component that you can see here going on the 5-axis is actually the cover for the accessory gearbox. So it's the front cover for the very forward portion of the engine structure. This covers up the gearbox casing. It provides the second half of the bearing mounts for all of the shafts that drive the gears in the accessory gearbox. And the front face of it is also machined to take the starter generator, the oil pump, the fuel pump, and the fuel filter and heat exchangers, and all of that stuff that we need to feed and service the engine. This is just on the 5-axis now to have the final features of those faces, flanges, and mounts all machined to the required tolerances. So this is the fully instrumented version of the combustor casing, the main structural element of the GT50 engine. As you can see, we've got the core cast component. This is a metal 3D printed prototype version of that. We've now machined the front flange, we've machined the rear flange, and then we've been in and machined all of the internal details to take the seals and all of the high temperature components in the core of the engine. The remaining operations on this are to run round on the 5-axis and just machine off the machining allowance and dress all of the mounting flanges for the fuel injectors, the service pipes and the various bits of instrumentation we need to monitor those critical first runs on the GT50 prototype. So in the last AMA, we showed you the range of rolled rings that we've produced so that we've got a stock of enough parts to make 3 prototype combustion liners. This is the very first completed GT50 prototype annular combustion liner. So it's got the head of the combustor here, which has got the floating springs to be able to seal the fuel injectors and the swirlers back into the unit. We've got all of the film cooling holes implemented. We've got the dilution holes implemented, and we're just waiting for a final op on this, which is pending the testing that we're doing on the combustion rig at the moment to choose the perfect position for the igniter plugs, and that'll put the last of the dilution holes in as well. We've also got the front end that includes all of those really difficult deep pressed sections that turn the flow round the corner and then throw it straight back at the face of the NGV to power the engine. So this is also now sat there ready to go. So another new part that's been recently completed is the interduct. So this is the part of the gas path that sits in between the exit of the gas generator turbine and the inlet of the power turbine, and its job is to just provide steady diffusion of the gas to stabilize it before it goes through the power turbine nozzle guide vane and turbine stage. So we've got these struts that go through to allow us to get services in and out, and then the rest of its job is to be a structural casing for the engine as well. So this is another part where we 3D printed it in super alloys and then machined it back here. So that we can get all of the necessary instrumentation, bosses and fittings in there. So that's just having its first inspection after we've done the machining ops, and that will then be nestled with the combustor casing when we start to assemble the engine. With all of the manufacturing now completed on the turbine blades, we've just been putting them through the final checks for dimensional properties before the selected few that will run in the first engine go off for final CT scanning, just to prove that any defects that are in there remain within acceptable tolerances. So that's just being completed ahead of assembly into the engine. And then what we've got here is one of the first blade liner rings. So this is the ring that the turbine blades and the turbine disc live within, and you'll notice we've now machined back the abradable coating that provides the close tip clearances we need to hit the efficiency targets and a safety margin against any rubs that we might see when we're really pushing the engine hard during development. One of the final parts that we're working on at the moment is the fuel manifolds. So these are cast components, so they're cast here at PC1, and then we have to machine them to create the passageways necessary to get the fuel from the outside world into the core of the engine and the fuel nozzles. Now, when we talk about machining operations, we're talking about the different stages that we need to go through to turn a lump of metal like that into a precision engine component that goes in the engine. So it starts as a cast lump here, and then we first machine the upper mating faces, and then there's some further operations on the underside of it, and then we go in and we machine the front face, which receives the swirler and the fuel injection nozzle. And you notice for each one of these things, you have to produce lots of different bits of tooling and fixtures to hold these weird and wonderful shaped components. The fuel manifold mounts on this flange on the outside of the combustion casing and transports the fuel into the fuel nozzle. So the fuel nozzle screws into the end of the fuel manifold like so, and then it's surrounded by the swirler. And the purpose of this is we let air from the combustion chamber go into these tiny little holes, and then it slides down, well, it gets pushed through these veined passages here to swirl around the fuel as it's injected through the center of the swirler assembly. And this helps atomize the fuel and then create the standing recirculation that we need in the primary zone of the combustion chamber to create stable combustion and a nice uniform heat distribution throughout the entire engine operating range. So nozzle goes into the back of the swirler, swirler goes onto the fuel manifold delivers all of that into the heart of the engine. Now, in terms of the fuel spray nozzles themselves, we've prepared a whole range of spray nozzles that enable us to tune exactly how the combustion system works on the final combustion test rig, Rufus 3, which we'll show you in a minute. Once we've got that set up just the way we want it and working well with the correct swirl distribution, then that's the hardware that we'll build into the first prototype GT50. So one of the longest lead time items of the build is actually fitting all of the instrumentation that we need to fit inside of the engine and getting all of that data out of the engine. So with gas path sensing, such as pressures, temperatures, velocities, all these sorts of things, we need to use rakes that protrude into the flow and then take measurements at different parts of the gas path annulus. On top of that, we then need to get those parameters out of the engine to a point where we can measure them and instrument them. So we have to run long lengths of hypodermic tube to transport the pressures and temperatures out of the engine to a point where we can fit the sensors and they'll actually survive. So this is some of the bracketry that we've had to design and manufacture to fit to various positions on the engine to allow us to measure everything we need to measure during the test campaign. The sensors that go with this are currently upstairs in stores waiting to be fitted. One of the areas of testing that we've been working on intensely over the last month or so has been the fuel and combustion systems. So you've seen our Rufus 1 rig previously, which is a single channel of our fuel and combustion system. We've been using that to prove out the nozzles and the ignition stability and to get the algorithms that we use to control the engine as close as we can on a single channel. We've now developed out, or we're developing out, the final stages of the fuel system that will be used on the full engine test rig and proving that on Rufus 1. And then we've now extended this rig to a 3 channel. So this is essentially a quarter of the combustion system. And in addition to basic ignition, fuel injector selection and scheduling, all of the control parameters for essentially the FADEC that we're developing out, then we also are able to look at the cross-lighting stability. So not all fuel injectors have an igniter. There's only 2 igniters in the engine, and so it's vital that we can cross-light between these streams. This rig allows us to prove out the exact positioning and operation of the igniters versus the fuel schedules and the airflows, and those are the parameters that we'll be using in the test engine. So this rig has just been finished and we're just assembling it at the moment. We're hoping to start testing on that later today or tomorrow, and I'll just quickly show you where they're fitting the combustion liner for this rig into the housing right now down in the machine shop. So if you imagine our annular combustion system straightened out into a long line and then we just take 1/4 of it, then that's this. And what you can see here is a straightened version of the combustion liner against 2 end plates. You've got the first stage dilution holes, the second stage dilution holes, the igniter port, and then these little holes that you can see here, here and here, the inlets for the film cooling to keep the liner cool while you've got the combustion products searing around inside there. So that's going together now. It will be fitted with the rest of the system up with the control system at the top end of the factory, and then we can complete the combustion configuration for the first engine test. Over the course of the last couple of weeks, you've seen us starting to fit out the test cell for the GT50 test program. Now, this is essentially a shipping container that we're repurposing. It contains essentially the test bench, which will be brought in here once we've finished fitting it out. The test bench itself has all of the containment necessary to contain a blade burst. And then as we go and do the later tests on the power turbine, we'll also build a concrete block structure around the outside of this to contain any potential disc burst. The container itself is lined acoustically so that we can cope with the high noise levels that are generated during some of the early gas generator testing, so that we can test for the long periods of time that we need to without upsetting the neighbours. The test cell itself includes all of the anti-vibration measures that we need to protect the engine as we start to run it, the electrical services, and of course all the data and instrumentation. The actual test bench itself is the original speed reduction gearbox test bench that's now being extended to include initially the gas generator, then the power turbine and the speed reduction gearbox that's already fitted, and then also the lubrication and the off-engine services we need to run the early testing. Many people said we had a mountain to climb to build our own gas turbine engine for HX50, and in fairness, I think they were right. We've now completed 99.5% of all of the manufacturing operations necessary to produce the components we need to start testing GT50. Every single one of them has been a difficult process, and our magnificent team have worked tirelessly to get this engine built. Within a week and a half, we'll be building the first one, and shortly after, we'll be starting testing the very first engine built for a helicopter in the UK in nearly 50 years. I'm super proud of what the team have done, and the fun is now really about to start.